Page 46, rotational matrix. I have a point in the coordinate system, then call it R. And this angle is. So what is the x coordinate and the y coordinate of this point? So let me also write it this way. R is related by x coordinate, y coordinate.
Okay, so it's R cosine X.
What is x? What is y? Yeah, good. Let's go.
R cosine X plus I. I'm sorry. R cosine theta. R cosine theta.
This is
Phi. I'm sorry. R cosine phi minus. Is it I psi too? No. It's not imaginary on this one.
and right now it's really just it's just a space position in space.
Okay.
So there's no imaginary involved here. Or you can rotate it in the imaginary plane, but yeah, the mass would be the same. So let's start with something that we can see.
Something exactly. Yeah.
Just imagine is east, south, west, north. Okay. So it's a map. Think of it as a map. And okay. So how can I apply a matrix to this x and y to make it a new x and y? It's a new x and y, and then you call it r prime. R prime. It's an angle theta. So you rotate. So what matrix give us this? Yeah. So what would be the new coordinate of x prime now? Would be if we rotate the magnitude is not going to change, right? So the length of the vector is not going to change. So it stay with as r. But its x coordinate is going to be phi plus theta. Y coordinate is sine phi plus theta. Agree?
Yes.
You just need to find, and this is my x prime. If you can recall, that's the question you brought to my office at the beginning of the semester.
Okay.
Do you remember?
No.
You said you were watching some video.
Oh yeah, the rotation of
Yeah,
the
that's it. That's
Okay.
it. Okay, so what a 2x2 matrix can give us is, so we can call it a rotational matrix, R matrix, acting on a vector R will give us a new R, which is the rotation of C. So we can do this here. So what is this one? So it turns out I can have R theta defined as cosine, sine, I think. Let me double check. Yeah, see, I'm right. So let's work on it and show how it works out. take the R out, right? So, cosine theta. So I have a R here and here. So why don't I just take it out? Okay. So what will be what kind of matrix do I have after I actually mark them explicitly mark them out?
Cosine
It's
squared,
2 by 2,
sine squared. Oh,
2 by 2 times
2.
2 by 1, right?
Right.
Okay, what do I get?
We're gonna get a 2 by 1.
I get a 2 by 1 vector. The first row, sorry, I made some mistake. This is phi, right? This is my x.
Okay.
Then stay already here. Okay. So this is x, this is y. Right?
Yes.
Okay. And the exponential work it out.
So, got cosine
You can do
square or cosine.
so when you do multiplication, you draw okay. Cosine theta, cosine phi, plus sine theta, sine phi. Minus sine theta cosine phi minus sine theta. That's cosine theta. Sine phi. Okay. So I might need to change it. So this is R. I'm pretty sure this one is cosine theta plus phi. So is this one sine theta plus phi? Did we just do that in homework 1?
Homework 1. I don't think that's homework 1. But I don't know. Yes, it was for this class. Class mixed up. Got it.
See,
So those are the two. Let's get it right. Cosine theta plus phi equals 2. just the formula we get from chapter 1. So this one actually, yeah. This one should give us this. Yeah, okay, so actually this matrix rotate this one in this next step. So, which also means I think this one, this one will rotate it in the for this. So actually we should have this. This is the matrix rotated in the. So this is the rotation matrix. This rotation matrix rotated in this direction. This is the rotation matrix rotated in the other direction.
Okay, cool. Okay. Nice.
Okay, and if I rotate them, so I change the sign of those two, then we rotate my R clockwise. Okay, another thing. If you do two rotations, first you rotate this way, and then you rotate this way, what are you going to get? You started from R, you rotate this way, and then you rotate in the other direction, the same angle.
You're back up where you started.
You're back to what your R is, right? So what does this suggest? What R times R transpose will give you. So if I multiply my R theta and my R transpose, or my R transpose times R, what should I get? You get back to what you started with. So what should be that matrix acting on your R? What should be this? you multiply a matrix to R and get R, what should be the matrix? You see, you have a matrix A times R equals R. What should it be there? Why don't you see it? You got it. That's right. We're gonna call it a 1.
The identity.
In matrix, it's not a number, the 1 is a number. But when you
Yeah, the
use
identity
a
matrix.
symbol 1, it looks like symbol 1. We'll call it identity matrix.
Mm-hmm.
So I'm expecting I should get identity matrix by multiply those two. So we can work out that explicit as well. Let's see. Cosine minus sine. And then cosine. Sine. Okay. So I should get a 2 by 2, right? So this is cosine square plus sine square. Agree? Now here is cosine, sine, subtract sine, cosine. What's that? Cosine, sine, sine, cosine. What do we get here?
Yes,
If I have to write what's split here is cosine theta, sine theta, minus sine theta, cosine theta. What do you get? It is 0. Right? Yeah, as expected. Now do the same thing here. Sine, cosine, cosine, sine, and then you cancel. Here is also I'm doing here, so sine square theta, cosine square theta. So it's indeed identity matrix, which I should get if I rotate it this way and then this way. You should have learned this right now in the polar coordinates.
Yeah, polar
in your
coordinates.
mechanics class.
Oof.
Yes, I get it. Something you learn and then flush.
Yeah, I'm going to be reserved enough. Hopefully not from me. The show from the tour.
Sure, got everything.
Ready?
Okay.
So for variable, we can have f(x) equals to 3 minus 2x squared minus x plus x to the 6. So if you give x a number, you can evaluate it, it will give you what are you get? You get a number, right? For whatever x, number x. So the question is, can I have a functional matrix? Like if I can 3 minus 2a squared minus a cubed minus 5a whole plus a 6. Okay, if I give you a 2 by 2 matrix A, after you do this, what I need to get? So this 3 has to become an identity matrix, right? So you cannot just add a number to a matrix. If A is 2 by 2 matrix, what is A squared? 2 by 2, A cubed.
Oh, okay, are we doing the, derivative?
No.
Okay, I'm ready.
This is just a 2 by 2 matrix times a 2 by 2 matrix.
Oh,
2 by 2 matrix, of course.
Okay,
Times another 2 by 2. So what power of A will stay as 2 by 2? But this is why when you do this, only the square matrix makes sense. If it's a rectangular, you cannot do powers. It doesn't make too much sense. Okay, so let's do one example. Let's just see my A is a very special one of my choice to make my lecture simple. Of course, it can be complicated. If my A is this, then try to evaluate what is A squared. What's this? 0 times 0 minus 1 times 1. What do I get here?
That's -1.
That's good. 0 times minus 1 minus 1 times 0. 0. They actually give me negative identity. So apparently what's going to be a cube give me? A times negative identity. Agree? Minus it? Then equals. This is the power of force. I, right? It's the power of this. You see the pattern, right?
Mm-hmm.
They keep going. So it's a A minus I minus AI, A minus I minus AI. Keep going forever. So now I keep this A, I keep my choice of this A. And I want to evaluate what is exponential. A number, a K, let's say. What is this? Can you put a matrix on top of exponential E? How are you going to evaluate that? No idea, right? Actually, it's allowed. it will give us meaningful result. In the end, we're going to get a 2 by 2 matrix. This is a special one. We choose it just to demonstrate so that we can do this. You don't have any homework on this topic. Taylor expansion. What is Taylor expansion of e to the x?
Start.
Have to rely on you now. Taylor expansion of e to the x.
Oh, e to x, e to x. I forget.
Google.
Yeah, Google knows all.
So it's 1 plus 1 over 2.
Oh, right.
It's just a 1 over 1. 1 over 1. X 1 over 2, x squared 1 over 3. Okay, if you Google, you'll find this expansion. So we're trying to write this one as 1 plus ka plus 2 plus ka 1 over 3 ka Q over 4 ka. So now, because of the padding here, a minus I minus ai, so I'm going to group every term with a together, every term with I together, right? So I'm going to look at this, all the odd power of a, give me a, or the odd even power of a, give me I. So I'm going to group all the even powers. For the even parts. Okay. Or the odd numbers of a together. And this will become 1 a squared equals minus I, right? K squared over 2 equals over 4. Do you agree? So the first term give me I, the second term give me minus I, this term give me plus I again, and then this term is minus I. 6. And this one gives me, I will take a out, this one give me k, this term give me k. Now Taylor expansion again, what is this? If you're familiar with Taylor expansion.
I don't know which one's which. One of them is cosine.
Okay, pretty good.
Yeah.
And it's
Sine is
simple.
negative,
It's simple.
cosine
You
is
just look at
positive.
the first term.
Mhm.
When x equals 0, which one is 1?
Oh,
Cosine.
that's cosine. That's
Yes. When x equals 0, 0, right? It's x. Sin x is x when x is very small. Now you're not going to forget. Great. Okay, so it's actually cosine k plus minus sin k. Yeah, you see, after evaluation, this thing that we think is impossible to evaluate give us something very simple, 2 by 2 matrix. Actually, it's a rotation matrix. Okay. Okay, so we're ready to move on to the next topic of this chapter. But this is really the most important, I think, the most important tool for physicists in linear algebra. Eigenvalues and eigenvectors.
Oh, yes.
Now, for those of you who are in computational physics last semester, you should you'd be able to help me teach this topic already. Everybody think so?
Yeah, you can.
After a little bit of review, sure.
Yeah, tell us what is eigenvector and eigenvalue?
an eigenvector
Mm-hmm.
is a vector that when multiplied by another vector doesn't change the value of that vector. It only scales it.
That does not change them. It changes the value.
It just scales it. Doesn't,
It doesn't change the direction.
yeah.
Direction just scales.
Okay. So it's good to write down your words. So I'm gonna add vector V. What does it mean? Act A on V. We get such that A times V parallel to V. So it doesn't change the direction of V if you're acting A. So if I give you a random, matrix, like and if I give you a random vector, do you think if I do this, the direction of the vector is going to change? So if I just do randomly, more than likely, direction will change, right? So the thing is that how do I find? And to be more specified, if I have A and V equals lambda times V scale, if you're acting A on this eigenvector V, it scales the vector by a number lambda that's called eigenvalue. So if you just randomly write down vector for a matrix, what the likely is not the eigenvector. So the problem is how to find. The problem is how to find the eigenvalue and eigenvectors. So we call this one eigen equation. So we need to solve it using this eigen equation. Okay. Now this tells us we can rearrange it. We can rearrange it in such a way that A minus lambda, of course, it has to be multiplied by an identity matrix to make it a matrix. We can nominate this a number. V equals 0. To make this equation has solution. Of course, you always have solution if you just choose your V to be 0, 0, right? If you choose your V to be 0, 0 is always the solution. But we're not interested in that. This doesn't give us any information. So we call this one trivial solution of this equation. So we want to find non-trivial equation. Solution to this eigen equation. But if you can recall that all linear equations has non-trivial solution. So how can we guarantee this equation has a non-trivial solution? You see, if there is a such a V, for example, let's just call it V1, V2, Vn. So I can just call this one a matrix M, and times N. If there is a non-zero V exist to make this equation hold, what can you see? something about the rank of n.
If M is a square,
Yeah.
it is a square matrix,
Uh-huh.
then it has to equal however many elements that are in the vector.
Mm-hmm.
So if it's at the end, it has to equal the end.
So the dimension of m is n. What should be the rank of m? Rank means how many independent rows you can have.
It has to equal or the end.
The problem is if, so we can do it the other way. If rank of n equals n, which means the n rows are all independent. If all the n rows are independent, can you find any coefficient multiply into these n rows and make them sum up to 0? Is it possible? No, because they're independent, right? Independent means you cannot. Yeah. You see, 1 minus 1 minus 1. That means they're linearly dependent to each other. 2, 3. They're not linearly. So for this, you cannot find any vector to make it 0 because they are linearly independent of each other. Linearly independent, which means you cannot multiply any vector to them. No non-trivial solutions. So which also tells us rank of n has to be smaller than n, right? Has to. And then what does it tell us? If rank m is smaller than n, then what's the determinant of n? What's the determinant of? If rank m is smaller than n, which is known that, right? What's the determinant? So which means you can do some row reduction. One of the row will become entirely 0. If one of the row is entirely 0, what's the determinant? 0. Yeah. So we'll call this one no word. Characteristic equation. So you just solve this characteristic equation of this for this matrix A, you'll find these eigenvalues. You can find these eigenvalues. Is still confusing? A little bit. Yeah, let's do example. Hopefully the example will take care of all your uncertainties or your confusion. So let's find eigenvalue of this matrix. So I need to write down the characteristic here. So determinant of A minus lambda equals 0. Determinant of This is A, right? Determinant of A minus lambda times I is 0. It is 1 minus lambda minus 4 minus lambda 3 minus 1, 2 minus 1. Oh, unedited, sorry. This is lambda times I. So see. And we know how to calculate the determinant of a 2 by 2, right? So it is 1 minus lambda times minus 4 minus lambda. Subtract 6 equals 0. Expanding. Lambda square plus 4 minus 1. So it's plus 3. Minus 4, minus 6, minus 10. So it's a quadratic equation. You can also quadratic equation, right? So I design the numbers and make it simple for me. So the thing I like to do most is factorization. So it's a minus 10. So I bet it's 5 times 2. Yeah, 5 minus 2 will give me 5 minus 2 will give me 3 here. Yeah, so you can rewrite this equation to be lambda plus 5, lambda minus 2 equals 0. Agree? So lambda square, lambda times minus 2, lambda times 5 will give me 3 lambda, minus 2 times 5 will give me minus 10. So the solution, well, the solution is lambda 1 equals minus 5, lambda 2 equals 2. So those are my two eigenvalues. Yeah, I think we do have time for homework. At least we can work out the homework 13 after we work out this equation. Okay, now we want to find out. So we can now write A times V1 equals number 1 V1. A V2 equals number 2 V2. Now because this doesn't change direction of V1, actually you can have infinite number of V1 and V2 as long as they are in the same direction. So the scale of V1 and V2 doesn't matter, it will always satisfy this equation. So remember, you could have infinite amount of solution to V1. So normally in physics, we will normalize V1 and V2 to be unit vector. So the magnitude is 1 for each angle. So now we can build this equation. 1, 3, 2, minus 4 equals 2 minus 5. Let me call it just a vector we're trying to solve. Minus 5, xy. Okay? Solve this linear equation. Give us x plus 3y equals to minus 5x. 2x minus 4y equals minus 5y. Did I make a mistake? Yes, in my notes it's just a typo. Yeah, that's right. So we need to solve this, right? We need to solve this. So the first equation gives us 6x equals minus 3y. The second equation gives us 2x equals no, it's not. It's minus y. Do you agree? So you see the first one? I just need to move this x to the other side. It actually give you minus 6x equals 3y. This one I just need to move this forward to this side. You see they're the same equation. It's the same equation. So as long as your y equals minus 2x is the solution. So which gives you your v1. So right now you can just choose your x to be 1 and your y to be minus 2. That's it. That's one of the eigenvector. And if you want to normalize it, you need to divide everything by 1 over square root of 5. Okay. So let's not talk about normalization yet. So this is less 1. Let's try to find what is point 2. So 1, 3, 2 minus 4 xy equals 2 xy. So the equation becomes x plus 3y equals 2x. 2x minus 4y equals 2y. This one gives me x equals 3y. This one gives me 2x equals 6y. You see, they're the same equation. They're consistent. So you can just choose your system. You can choose your y to be 1, your x to be 2. That's the eigenvector. So you can. Now at this time you can plug it back your 3 and 1 back. You will see this equation indeed holds. You'll find your eigenvalue and eigenvector. Any of you volunteer to work on the next homework program on chapter 2? So if you work it out, then yeah, everybody can free to go and enjoy the rest of the day. Why are you always looking at everyone? That costs them more.
No, I'm not talking. Hold on. Let me look at it. Hold on. Let me look at it. Let me see.
And you want to give it a try? Homework is 13. Find the eigenvalues and the eigenvectors of a complex matrix. The only thing different is it's complex. But you just follow the same procedure. Exactly follow the same procedure. That's the only thing you need, right? That's the only thing you need. Determinant is 0.
Okay. Yeah, no. I ain't built for that yet. I ain't gonna lie. So, yay.
This is called the Hermitian matrix, which means
Hermitian.
if you do a complex conjugate,
Good.
if you do a complex conjugate and then transpose it, give back this. The nice thing about Commission matrix is that the eigenvalues are always real, even though it's a complex matrix. So let's find the correct equation. So it's 2 minus lambda minus 1 minus lambda 3 minus I 3 plus I. Two minus lambda minus 1 minus lambda minus so 2 multiply is going to give me lambda square minus 2 plus 1 minus 2 plus 1 is minus 1 minus 2. Okay. Read out here. So we say use the same trick I have. Looks like 3 and 4. 1, 1, 3 times 4. So 1 minus 1 should be 2. So it's lambda minus 3, no, plus 3, lambda minus 4. Agree? So lambda will give me lambda square, minus 4,
Negative
plus
12.
3 give me minus 1.
Minus lambda. Negative 12.
So I found the two eigenvalues. One is minus 3, another one is 4. And put it back to find out what's the eigenvectors. So it's 2, 3 minus I. Now the eigenvector is no longer required to be. It could be x, y equals to minus 3, x, y. So this gives me 2x Alex. Equals to minus 3 plus I, 4. Okay. And this will be 3 plus I. So I bet this is a solution you can just, it depends on you. You can choose your x to be 1. So if your x is 1, so for this one, where 1 is, x is 1, your 1 is going to be 3 plus I. It's the first time you make. You can do the same thing. You can do the same thing to find what's the eigenvector of this one. When you do this one, okay.
All right.
Yeah. Yeah, you should just start working on chapter 2 homework. Nice pattern, right?
Yeah.
You have one set of homework due from one of the 2 classes every week.
Yeah. That is nice. Okay.